Welcome everyone. This is the second part of my lecture on neural networks and deep learning. And so far I covered models which follow the so-called feed-forward architecture. So data are presented at the input and then these propagate through the layers of the network. There are no other connections. So today I'm going to talk about two different models. The first one is based on the use of recurrent nodes, which are combined to form recurrent network architectures. These nodes have feedback connections, so the previous state of the node is used as one of the inputs. And then talk about another kind of approach, which is used in the so-called residual networks. These networks use blocks of layers. These are called residual blocks, and these are combined with direct links or skip connections, which bypass these kind of layers, transferring signals from previous phases of the network, stage of the network, directly to the next layers and to the output. Finally, I will have a few things about ensembles. They explain the notion of weak learnability, which is behind the operation of ensembles, and present different kind of architectures that we can use to build ensembles. The figure you see at the bottom, it's an active link you can find in the slides. It's the link to a video that is already on Moodle and explains what is a neural network in case you want to quickly go through that. So today about recurrent networks, we'll start with the model of the linear neuron. It's a linear neuron, so the activation function is just linear. There is no sigmoid or other kind of activation. And this node has a feedback connection. So the output of the node is goes through a delay element and is multiplied with a weight. As you can see, the node has an initial state. This is A0. There is again a bias, and the output is produced. So this delay element allows the node to remember the previous state. So the current state is called n+1, and the previous state is an, and the state is multiplied with a weight. The operation of this simple linear node with recurrent connection can be expressed by this kind of equation. So the state of the node is the previous state times a weight plus some bias. And we have to specify the starting point, and in this case, the initial state, the state of the node at n equals 0 is 0. Okay, so the operation of this node can be explained with a very simple example. Okay, basically this kind of node is going to generate a sequence of iterations, a sequence of activation of values, a kind of trajectory in the space. And depending on the value of the weight, this kind of sequence will converge or diverge. And I have an example here to show you how things work. For example, the first case, this is the operation of the node. That's the value of the weight. And that's the sequence that is generated, xn+1. The point on the next iteration is equal to the weight times the current state plus 2. In the second equation, you see that the weight changes, and it has been shown in dynamic systems that even for this simple model, we can generate completely different behaviors. So the first equation will allow the sequence to converge to one value, the value 2.5, as you can see in this table. The second sequence, because of the different value in the weight, it's going to diverge completely. So at each iteration, a new kind of number is produced, and the node will diverge, will not converge to a steady state, we say. So for this simple sequence, there has been an analysis, and we can see that it diverges or converges depending on the values that we are going to have in this parameter here. These kind of systems, which are represented by this form of equations, these are called difference equations or recurrence relations. They are called discrete dynamic systems. So in discrete dynamic systems, we generate at the output a sequence of iterates depending on the previous state of the sequence. So this process is repeated continuously, and we go through different type of iterations, we say. So here we have, for example, in my example, we have 9 iterations, and 0 is the initial state, and then we have 9 iterations. And you can see in the table how the value of x changes as we move from iteration to iteration, and the new value will depend on the old value, which is multiplied with the weights plus this kind of extra term, which is like, a bias. These kind of systems are not new, are not, do not only exist in the world of machine learning. I have an example here which follows the same kind of idea. So it comes from finance. So as you can see here, Adriu is 18.5 years old, won 20K in the lottery, invest this kind of money in an account with fixed rate of interest, 6.5, which is compounded annually. And we want to know how much money Andrew is going to have on his 25th birthday. So if we want to use to do these calculations, basically we're going to follow a kind of recurrence relation, and which is going to produce a sequence of values. And you can see that this is the first step. It's the initial amount plus interest after the first year. And then we have the amount at the end of the first year. Then at the end of the second year, we have the initial state is the amount we had in the at the end of the last year, plus the percentage of interest multiplied with the amount of money. And at the end of the nth year, it's actually what we are doing is that we are following this kind of sequence. So the new value is the old value plus the amount of interest time the previous state. Okay, so it's another case of linear dynamic system, which is expressed by this form of iterative equation, iterative relation. And what happens here is that you can see the sequence that is generated. N0 is the initial state, the initial amount of money, 20K we said, and that at each year, these are the iterations from 1 to 6. I have on this table, you see how the amount of money changes. Each value represents a kind of point of this sequence which is produced as time goes by. Okay, and the whole process is represented by this equation you can see on the slide. So this kind of equations, they represent the behavior of a discrete dynamical system. And in general, we say that we have the state, at the next iteration, the state of this system, x, equals with a function which depends on the previous state. This function is called a map or iteration function of the system. And if this function is linear, then we have a linear dynamic system. If this function is nonlinear, then we have a nonlinear dynamic system. These kind of ideas have been used in the world of neural networks to design a different kind of dynamic neural networks or recurrent neural networks. Recurrent neural networks is a special type of dynamic neural network where again we have this notion of layers, because you can design dynamic neural networks without, the notion of layers and connections from one layer to the next. Okay, you can create much more complex dynamic networks, neural networks. So the general form of a linear difference equation of this form, as you can see in the slide, is xn plus 1, which is equal to b times xn plus a, and a and b are constants in general, and then you have this linear map fx, which actually defines this combination of a plus bx. Okay, so obviously in a neural network, this function f depends on the type of activation function that we are going to have. And I have an example here of a linear recurrent neuron. This neuron generates a sequence which uses this kind of equation. So AN is the activation level of the node, the output of the node, at n plus 1. And this is produced by the value, the previous activation, AN, times a weight, W, in this case is 0.8, plus 2, which is the bias. A0 is the initial state of the node. Okay, so this has to be given or has to be defined. So this kind of equation is going to generate a sequence of points that follow this kind of model, starting from the initial value A0, and it's going to create a kind of trajectory or orbit which follows the mapping F. And this kind of trajectory of the dynamic system is going to reach a certain state. This is called fixed point. And when it reaches this state, this fixed point, it converges. Okay, if the value of the parameters do not allow it to reach a fixed state, then it's going to diverge, and it will be impossible to control the operation of the particular node. Okay. Obviously, neural networks reaching fixed points is clearly very important, not only for neural networks, for other kinds of dynamic systems, because otherwise the system is not stable. Okay. In the case of neural networks, the fixed point represents a kind of memory that the system has learned from the examples, and this memory can be retrieved from the network. I have an example here from an old dynamic network used in a project 20 years ago. It shows you how the activity level of the different node changes. And in this particular example, you have nodes which generate a sequence of points. The sequence of points is represented by these circles or crosses. And we have 30 iterations here. So you can see that some of these nodes, they start, for example, from a value close to 0.2, and they produce a sequence of iterates that converges to the value plus 1. Other nodes produce a sequence of iterates that converges to the value minus 1. Okay. But as time goes by, the node that has received an input and has an initial state, it will follow the model and reach a stable state. If the state is stable, it means that if we give a small displacement from this initial state, then the node is going to return to exactly the same fixed point. This kind of behavior in dynamic system is represented by an attractor. We say that the fixed point of the system is stable, and it is an attractor. It attracts inputs which are very close to the state in the neighborhood. Although there are small displacements from what this node has learned, it will return to a stable state. If that doesn't happen, then the node will move away from the stable state, from the fixed point. So it will become unstable. And according to dynamic systems, this kind of fixed point, this kind of state is called a repeller. This kind of behavior is important for neural networks as well, because we see situations like these cases when we use adversarial examples. So you have networks which have been trained, and they are very good at recognizing different kinds of objects or animals in this case. And you introduce a small variation and a small displacement from from the original states by introducing a small amount of noise, and then the behavior of the network, the information that is retrieved from the network, is completely wrong. So, for example, these are classic examples from the literature. So this network receives at the input a panda, plus the photograph, the image of a panda, plus some kind of noise, and then it recognizes the animal as a gibbon. In this kind of situation, the input is a meerkat, and then some kind of noise is added, and the output, the network believes, generates as an output that the object that was presented, the image that was presented, is a doormat, okay, a welcome mat. Okay, so this there has been a lot of work in the literature trying to analyze the behavioral networks in the context of adversarial examples and how we can create robust models that will not be tricked by small displacements or small variations in the input data by injecting carefully noise in the image, and we'll be able to retrieve memories, images they have learned successfully. So let's have a closer look at how things work in a recurrent neural network architecture. A recurrent neural network will consist of a large number of recurrent nodes. These are normally recurrent neural networks organized in layers, like in normal feed-forward neural networks. But each one of these nodes will have some kind of feedback, like in this case. So it remembers the previous state. And mathematically, this can be given by this equation. So that's the output of the node at the time at the next iteration, n+1. It depends on the activation function and on this weighted product, which is W, which is the weight by which the input signal is multiplied, plus another weight, it's called G, by which the previous output of the node yn is multiplied. So this is the equation that describes the operation of the node, but obviously the situation becomes much more complex because we have several nodes organized in layers, and also we have several layers, in particular in deep networks. Okay, so if I want to do a simple calculation to see how the sequence of output is produced, then I would have to go through this kind of calculations to calculate the forward propagation of the values. So that's the general model, and then we have output at iteration 1 depends on the input x at point 0, that's the initial data, the initial input that the node receives, and the state of the node, that's the output at time or iteration 0. And this will give me, allow me to calculate what will be the output of the node at iteration 1. Then I can use this information to do another calculation to produce the output of the node at step 2. And then use output at step 2 in order to do another calculation and find the output at step 3. This is how it's going to work internally. One trick that you might have seen already, in different blogs and websites, is the so-called unfolding or unrolling. Unfolding is the term mostly used of the node in time. So the operation of the node is, it's represented by this feedback connection plus an input, the current input, and the feedback, which takes into account, plays a role of the memory. It introduces as an extra input the previous state of the node. And the idea is that instead of using this kind of model with the feedback to unfold the node in time. So this kind of schematic here shows you the unfolding of this node in time. It gives you 4 time steps. So you have what happens at the beginning. This is time 1. It produces y1. I showed you the calculation in the previous slide. This output then is used as one of the inputs together with the input at the next iteration, x1, and produces the output of the node at time 2. And we go like that. At time 3, we produce another output, which takes into account the new input plus the previous state. And then we have a time t equal 4, the fourth time step, we can produce the output of the node. And that's why at time 4. Okay. The same kind of operation could be represented by this simple node by monitoring, the trajectory for 4 time steps. Okay, or you can represent it in by unfolding the node in time. Okay, this is unfolding in time for 4 steps of one node. Okay. Obviously, the situation becomes more complicated if you have networks with many nodes, recurrent nodes, and you want to unfold not 4 time steps, but I don't know, 100 or 1,000 time steps. Okay, it depends on the sequence. So basically, what we say is that the one node, by unfolding the node, the operation of the node in time, what we have is just a feed-forward neural network. Okay, so this is just one node. One recurrent node unfolded in time. It will become like a network with 4 nodes in this case, because I have 4 time steps. Okay, so each time I run a step, it's like introducing a new node. Or if you have a network, a new layer. Okay, and that new node is going to have an input, external input, that's X3, for example, and an input which comes from the previous activation of the node at the previous time step. Okay, and that will allow it to produce the output. Okay, so a new layer will going to be, or a new node will create it each time step as the node does the processing of the input data. So since we can unfold it and we can produce a feed-forward network, then we can train it like a feed-forward network. So we give a sequence of data at the input, x0, x1, x2, x3, depends on, it's a time sequence. And then we have some initial state, initial conditions, as usual for the weights and the activations. And we can compute a sequence of outputs, y1, y2, y3, y4. Okay, and that, since it could be represented as a feed-forward neural network, as one can understand, someone could use techniques like backpropagation to train it. It will be much more complicated than a normal network because we have this unfolding, but it is done. It can be done with this technique. So we are going to have, if we use kind of backpropagation, then we are going into supervised learning, which means that we have some desired output. So we have a vector of desired outputs, it means that basically that at each time step, we know that what the desired output of the network will be, and we can use it to calculate errors, like I have done in this case. Okay, remember that this is just one node, okay, unfolded in time. And I assume that someone has given me the desired output, so I can calculate all these kind of errors. The figure you can see here, it's a link again, you'll find it in the slide. It explains how the backpropagation works mathematically. This kind of idea that you can see on the slide about the unfolding of the network follows the same kind of concept, basically. So let's assume now that we have a trained network, and we want to see how it operates. One of the big advantages of these models, there are different kinds of architectures, obviously, for recurrent networks. And some of them you might have heard already, they have produced excellent results. If you have seen the videos that I have and the links on Moodle, produce excellent results in natural language processing, for example. Okay, what I have here is a very simple model, but even simple models can show you how they can make predictions of, and it can generate sequences, and they can predict what's going to happen next, basically. Okay, so in this case, it's a very simple network, and we want to generate a sequence. The sequence is A, B, has some kind of letters. And to keep it simple, we have just two patterns, two letters A and B. A is represented by a vector, 1, 1, and B is represented by another vector, 0, 0. And that's our recurrent network. And we assume that the network has been trained somehow, and the value you can see at the figure are the weights and the biases. So this value 1, it's the weight of this connection, -2, it's another weight of connection, and in the center of each circle is represents a recurrent node, and the value that you can see in the circle is the bias of this particular node. And these are the input nodes. The input nodes receive some initial inputs. The initial inputs, in this case, the initial input is a vector 2, 2. So these two nodes, each one receives a signal which is 0, and that triggers the network, and it starts generating the sequence of iterates. We assume that this is just at the beginning, and then the input nodes do not receive additional inputs. To make it simple, from the environment, they just receive the internal inputs which come from other nodes of the network. So for example, the input node, this input node will receive input from the output node, which is multiplied with a weight of 1, and then it has a feedback loop, which is these nodes' previous output, previous state, which is multiplied with a weight of 0.5. Okay, we assume that the nodes, the input nodes have linear activations, so there is no nonlinearity in this case. There is a hidden layer which has one node. This node has a bias of -3.5. It receives inputs from the input nodes and transmits its state or the output to the output node. This node has an activation function. It is a binary threshold activation. So it's going to produce, it will be activated, will produce a positive signal at activity level at its output if the total input that it receives is bigger or equal to 0. Okay, and binary threshold outputs, also activations are used for the output nodes, as you can see here in this figure. So let's see how this thing is going to operate. And I have this table here to show you how this model is going to work. The rows represent different time steps. And you can see input 1, it shows you what the node, the input node 1 and input node 2 are going to get as inputs, what's going to be their output, and then hidden shows you the behavior of the hidden node, and output 1, output 2 show you the behavior of the operation of the two output nodes. So at the first time step, the input of the first node. The first node we said is going to be triggered momentarily by a signal from the outside world. It's going to be 0. And we said that the initial state of this node is also 0. So this is the two zeros you see here. So it's 0 plus 0. The first 0 comes by the output, which was 0 multiplied with 0.5. It's going to give you 0. And the other 0 comes from the initial X signal, which is, we said is going to be 0. So this is going to produce at the output a signal of 0. Same kind of thing happens for the second input node. And then we have two zeros as a result at the output of the output of the input nodes, and these are multiplied with weights of 1, and they form the input of the hidden node. So the hidden node is going to have an input of 0 minus 3.5. That's the threshold we said, and because it's a binary threshold activation that is used, the value is negative. It's smaller than 0, so the output is going to be 0. This output is going to be multiplied again with weights, -2 in this case, no change. It's going to give a 0 signal to the output node. The same thing happens for both output nodes. So the state of the output node, it's going to be, it all basically depends on the bias that the node has. We said that the bias of these nodes is 1. So this is going to give you 1. So both our output nodes are going to be triggered. They will produce a value of 1. And we said that 1, 1 is a representation of letter A. Okay, so this is how the first output of this network is generated. It's going to respond with the letter A. And then the signals are propagated through the feedback connections of the node, and we go to time step 2. In time step 2, you see that things change. There is no external input anymore. In any case, the external input, we said it was 0. So this kind of node, the input node, is going to receive a 1. That one comes from the feedback connection that the node gets from the output node. The output node, we said, produced 1. So this one is going to be multiplied with the weight of that feedback connection, which is also, again, 1. And this is going to give you the 1 which is used here, plus the value of 0, because that was the activation. Here you see the activation value of the node at the previous time step. Okay, so we can do that, and we're going to get the new activation at time 2 of this node, which is going to be positive in this case. The same happens for the second input node. So now the hidden node receives positive signals from both input nodes. These are multiplied with weights again. So in total, it's going to receive a positive activation from the input layer. The value is 2, but we said that it has a negative bias, which is minus 3.5. As a result, its output is again negative, which means that because of the threshold activation function, is going to produce a value of 0 again. This 0 will be propagated to the next layer of the network after multiplying it with the values of the weights, which are minus 2. And we're going to get, again, outputs of 1 and 1 for the 2 output nodes, which again represent the letter A. So we work like that, and we produce outputs which are going to feed the nodes in the third time step. At the third time step, going through the calculations, the network is going to produce again the value of A, feeding the outputs again into the inputs. As again, there is no external signal, we said, so the internal nodes, the 2 input nodes, just receive inputs from the output nodes, and they just remember their previous state. So what we get here is finally a change. There is some kind of activation. Signals become larger because the nodes get the previous output was 1.5 times 0.5 the weight, it becomes 0.75, plus a positive input from the output node, which increases the level of activity of the input units. These activities are multiplied again with weights, and they give you a large value. Now the value becomes 3.5, which can compensate the negative bias. It will give you a value of 0, and because we said that we are using binary threshold activations, which produce an output which is 1, if the signal is bigger or equal to 0, finally, this node, the hidden node, will be activated. The output will become 1, and then multiplying with weights, it's going to trigger again the output nodes, and as a result, the output that will be produced will be 0, 0, which is a different response. It's B. Okay, so this network actually has produced so far a sequence of letters. We said that it's simple. It only knows, has been trained has learned only to represent 2 patterns, A and B. So it can only produce sequences of this kind of with 2 letters. So it was going to produce the sequence so far to produce a sequence A, B. Okay, and if we go like that, we can continue with calculations, and unfold the response of this network in the 5th time step, 6th time step, etc., until we can see that it converges somewhere. The good thing with the advantage of this kind of networks, and this is the reason people have have started the investigation of this kind of networks since very early in the 80s. There was a lot of work on dynamic networks and recurrent networks. But it's, training this kind of model is not trivial. It's much more complicated because of this kind of unfolding, which increases the dimensionality of the network. So the advantage is that you can design networks that can produce indefinitely long sequences of actions. And they can behave in a deterministic function. So given an initial state, only a sequence of actions can be produced with simple models. But the good thing is that we can make it learn much more complicated sequences. And there has been a lot of work again in the 80s and 90s to produce new kind of models that will be able to have this kind of behavior. The problem that we had at the time was that we couldn't train this network for long, and we couldn't solve very difficult problems because we didn't have the computational power. So this is another architecture that was introduced by Michael Jordan, who did work in neural networks in the 80s and 90s. It's a recurrent neural network which has plan units and state units. So what happens is that, as you can see, it's a kind of feed-forward network, but there are also feedback connections. The feedback comes from the output nodes. He introduced the so-called state units, which remember the output state of the network. And these state units can also have feedback connection as well, and they used as extra inputs in this kind of architecture. So the network receives inputs from the environment. These are called plant units, but there are also these state units which remember previous activities, previous states of the network. And people have shown that this kind of network is capable of learning much more complex sequences. Really, the game changer, perhaps, in this kind of area, in the at the end of 80s and very early 90s, was the introduction of Ellman's architecture. Ellman produced a paper, Finding Structure in Time, and that paper made a huge impression at the time. He introduced this idea of context units, and he applied this kind of architecture in language learning. So the idea of context units is that you have units which store the activities of the hidden units for one time step. At least this is how it was introduced. It is possible to have bigger memories and remember not only the previous state, but other steps back as well. So you have input units and you have the context units, which remember the previous states of the network. Ellman suggested to use fixed connection weights for the feedback connections. And this network can learn any sequence that is given as input. And he applied this kind of architecture to make predictions, to train the network in prediction tasks. The idea of the introduction of these context units is the thing that make that network to behave differently, so depending on the context. So for the same kind of input, the network recognizes the context because it has the context units and adapts the output to the context, although the input may be the same, okay? So we have identical inputs which are treated in a completely different way because of the current context. The original architecture that Ellman produced was generalized. That's the so-called layer recurrent network. It's standard in many toolboxes libraries that we have today. So it remembers the previous state of the hidden nodes, of the hidden layers. And you can have that if you have many hidden layers, okay, you can have several context units, in a sense, which give extra inputs generate extra inputs to the layers of your network. Another interesting concept, again introduced in the 90s, is the so-called autoregressive, non-linear autoregressive recurrent network. Okay, in the autoregressive recurrent network, what you have is that you have again context units which remember the context, but this is not the context of the input of the hidden nodes. It's the context of the inputs. So you have the inputs at time step t, but you use as extra inputs what happened at the input at t minus 1. Okay, so you, in a sense, you increase the dimensionality of the input space. So you don't have only the current word, but you also have the previous word, in a sense. And then another interesting feature is that you use also, as an extra piece of memory, the states or outputs of the whole network. So you take into account the activations of the output nodes. And these are used, again, as extra inputs, okay? These are the autoregressive models, which have some very good properties. They can model dynamically changing contexts. And one of the advantages is that they are trained fast enough with respect to other recurrent neural networks and dynamic neural networks, obviously. Because as I said, training this kind of networks is difficult. One of the methods that is used, it comes from the backpropagation. Is a variation of the backpropagation that have been produced for recurrent networks. It just follows the basic backpropagation rule, and you have to calculate, again, derivatives. This recurrent version of the backpropagation is called backpropagation through time. And it operates by doing this kind of unfolding, which I mentioned before. So we unfold the node or the layers of the neural network. So in my background, for example, you can see the figure which I have at the back. It's an unfolding of a recurrent neural network in time, okay, for 3 time steps. So this is what you have here. You have the unfolding of the node for 2 time steps. Assuming that you are given the desired outputs, you can calculate the errors. So what happens every time is that we present data to the network as a sequence, as a time sequence of inputs and desired outputs. And we do this kind of unrolling or unfolding. We calculate the errors. We accumulate all these errors at each time step. And then we roll up the network and we update the weights. And we do that at each time step because it's a time sequence. And I have here a very simple version of the backpropagation just for this simple network, for this node, basically. This is just one node unfolded in time. So you can see how things work. So this kind of node has weights. These weights are represented by W's and G here. So W is the weight of the input, multiplies the input with the weight W, and this is G is the weight that is used to multiply the previous state or previous output of the node. Okay, so we need to calculate updates for W and J, delta W and delta G, basically. Okay, and this is what you see here. So we have, as we normally do in feed-forward networks, first we have to calculate the weights of the output nodes, connecting nodes between the hidden node and the output, the hidden layer and the output layer. And this is what happens here. So these are the W, G, and W2 and G2. That's the number of the layer. So these are these two corrections for W and G of the second layer. Let's say this is the second layer, and this is the first layer. So this is the calculation of the corrections. It takes into account the learning rate, that's the eta, the errors, the outputs, and the inputs. And we do the same for the G. And we use the error in this case, which is the difference between the output of the node and the desired output. And here are the weights of the first layer, delta W1, delta G1. Again, the learning rates. These are the initial, the inputs this is the input of the node, and this is the initial activation of the node. And this is multiplied with this parameter delta, and you can see the delta here. It's much more complicated. It takes into account the activation of the node at time 1 and the errors, etc. And remember, this is a linear node, so there is no non-linear activation function here to make things simple. In reality, we have networks with non-linear activations, sigmoid, tangent activation. You can have recurrent convolutional networks. So the situation is much more complicated, and that's why we appreciate the use of all these packages that automatically differentiate, do the calculations, and they produce the derivatives. Okay, they simplify the task, otherwise a very complicated process. And as you understand, this backpropagation in time can be computationally expensive as the number of time steps increases because of this kind of unfolding. Okay, so if you have input sequences which have thousands of time steps, because you have data points which are presented, one after the other, a stream of data, the number of derivatives required for just a single weight update, it depends on the number of time steps. Okay, so in a network you have millions, in a big deep network, millions of weights, and if you have a long data sequence, then the calculations are enormous. Another problem you have, which is not just the computational complexity, is the problem with the vanishing weights or exploding weights. So you can have weights which become very small, they become zero, or you can have values which become very large, and that affects the way the nodes operate, basically. Okay, the implication is that some nodes are led to saturation. It's called the dynamic systems. So they lock in a particular state and they cannot change, no matter how hard you try, if that happens. Okay. And in the literature, in neural networks, you can see this kind of situation with the terms, people referring to this kind of situation with the terms vanishing gradients or exploding gradients problem. The gradient vanishes because you have all these long sequences and you do this kind of unfolding, and the values of the gradient may become very small as it propagates from layer to layer backwards. Which means that the weight corrections become very small. They become zero. So the weights, they don't change. They can become very small, or they start, the sparsity of the network increases, which causes serious problems in the computations of the training of these kind of models. One trick that people do, it's a standard process nowadays, is to try to reduce the dimensionality of the input data. Okay, so if you have a long sequence, you cannot use all the time, the data of the time sequence, input sequence that you have. Okay, there was one of the first papers that identified this kind of problems in 1990, as far as I remember. You can find it online. Learning long-term dependencies is difficult. Okay, if you Google, you'll find it. Okay, by Bengio, one of the very important papers that he wrote. Okay, learning long-term dependencies with gradient descent is difficult, and he analyzed this kind of problem. Okay, how difficult it is to model long sequences. Okay. So the trick that we do to reduce these kind of problems is to use a sliding window. It's not a new idea. It's not something that was designed for neural networks. It has been used in signal processing since, the 60s, this kind of idea. So you defined a window length and you slide the window length along the sequence that you want to model, basically. Okay, and that reduces the time of time steps and reduces, in a sense, the computational complexity of the problem. I have an example here from one of the papers that we did when we tried to model signals from smartphones for Parkinson's, from Parkinson's patients. I have referred to that example before in another lecture. So the time sequence here comes from the accelerometers, which measure acceleration along 3 axes, X, Y, and Z. So you have these 3 sequences here. And, someone could say, okay, I have a long sequence. The more signals I use, the better. Unfortunately, yes, okay, but in practice, you cannot do that. You have to specify a window and slide that window in order to reduce the complexity. The good thing is that these kind of things work in practice. So we define a slide window of length W and feed the network shorter sequences. Usually there is an overlap between the sequences, and this is the trick that we did here. So we have a sequence of 256 time points, that's the length of the sequence, and we have a window, the overlap between windows is 128, okay? So you have overlapping windows of 256, and the overlap, as you can see, is quite big. It's 128 time points. And that thing allowed to train the network. And in this case, we used a recurrent convolution. So we use recurrent layers, which had convolutions and recurrent connections. It's an architecture that has worked very well in signal processing applications. And we find it work well in this case as well. Okay. Let's move now to another kind of architecture. It doesn't use feedback connections. It's a different idea. It's called residual network, introduced later in 2015 by some researchers working for Microsoft with a paper, Deep Residual Learning for Image Recognition. They applied this idea to image recognition applications. Actually, that year they won the first place in the ImageNet competition. They were best performers for the ImageNet localization task, the COCO detection, and the COCO segmentation datasets. The idea, what they did is that they introduced skip connections that bypass the so-called residual layers. I will explain what they mean by that, which allows data to flow from any layer directly to subsequent layers. This idea, no matter what they believe, it's not new, sorry. It's the idea of using direct or skip connections, which people have tried to use in the past. In much simpler networks, because in the 90s it was not possible to train these big networks. So one of the first papers was in 1990, where genetic algorithms was used to train neural networks and optimize the connections and the connectivity. And in that work, after optimization with genetic algorithms, they managed to produce architecture which had this kind of direct connections from hidden layers to output layers, and etc., depending on the result of the genetic algorithm. In 1994, with this paper, Fit for Artificial Neural Networks for Solving Discrete Multiple Criteria Decision-Making Problems, the researchers proposed again an architecture. They found out experimentally that by using connections from the input layer to the output layer, bypassing the hidden layer, work better. Train the networks faster and produce better generalization. An interesting work is in 2013, actually, analysis of multi-layer neural networks with direct and cross-forward connections, where there is a theoretical actually analysis which shows that the use of this kind of architectures, which have connections, direct connections, or cross-forward connections, as these researchers call it, because you can connect bypass layers and connect, the third layer with a sixth layer, if you like. They provide theoretical justification of why this thing can help with training and generalization. And as you can see, this work came much earlier than 2015 that the deep residual network was introduced. And then we have in 2016 another idea, the so-called dense convolutional network, which of course is computationally much more complex than the residual network. It allows connecting all layers directly with each other. Okay. So each layer obtains additional inputs from all previous layers and passes all the outputs to all subsequent layers. A nightmare computationally, but they have found that they produce very good results. Complexity is higher, in my opinion, because I've used residual networks. They are great. One of the best architectures. The whole idea is based on this thing, which is called the residual block. So you have a combination of two layers. These two layers define the residual block. And the residual block basically creates a kind of function. This is called the residual function. The exact form of the function obviously depends on what kind of activations these kind of layers are going to have. Okay, and then what you have is these direct connections or skip connections from the input of the residual block to the output. So this is the input signal that the whole block receives, and this bypasses the block and is added to the output of the block. Okay, and there are different ways to exploit this kind of information. You can use it as a direct identity mapping, which means that you don't have a function H here. So you just add the input. Okay, or you can do different kind of tricks. You can have a function here. This function H can be a convolution, if you like. All right. So different people, different researchers try different kind of combinations. The good thing is that just using the identity mapping helps a lot, and it makes calculations simpler than using, obviously, activation functions like convolutions at this step. Okay, so they have found that identity mapping achieves faster error reduction, and at the end it can produce into lowest errors just by using bypassing the function and just passing the input and adding the input to the output of the residual block. Okay. Then you have the classic ReLU function here, rectified linear unit. And again, people have experimented it in different ways. Some people they add the output of the residual block with the input X, and that goes through the ReLU function. Other people have done in a slightly different way. They first apply to the output the ReLU function and then add the input. There are different ways, but in general, this kind of combination works well. You can see it here in this kind of equation. So you have F can be a rectified linear activation, and then you have H, which depends whether you're going to use a convolution function here or not, or you're going to use just the identity mapping. If you use the identity mapping, then the whole situation will be much more simple, as you can see here by this equation. So you produce XL plus 1, which is the next layer, is going to fit the next layer, which is equal to XL, which is the input that this residual block is going to receive, plus the function of the whole block, the operation of the two layers. This is the definition of the residual block. You need at least two layers, okay, to create a residual block. And then you can see whether you're going to apply rectified linear activation or not, okay? There is another interesting result. It came later in 2016. So these guys here in this paper, residual networks behave like ensembles of relatively shallow networks. They actually show mathematically that this kind of interesting architecture, the residual network, can be unfolded into an ensemble of 2n-1 smaller networks. N is the number of blocks. It depends on how many residual blocks we are going to have in your architecture. Okay, so they showed that a residual network can be unfolded into an ensemble of simpler networks. which actually is another way to explain why this kind of architecture works well. Because we know that in general, ensembles enhance the performance in terms of generalization of simple models. And I will explain how ensembles work next to explain why this kind of behavior makes sense. So let's move to ensemble learning. Ensembles have been introduced to increase the general performance. And there are different ways of ensembles. You can combine different kind of models, for example. By unfolding the residual network, you basically use the same kind of simple architecture in the ensemble. But in general, an ensemble can consist of different kind of models. So you could combine an ensemble with different kind of architectures, not only necessarily neural networks or deep learning architectures. You could create an ensemble by combining completely different models like a neural network and decision tree or a nearest neighbor classifier. There has been a work again in the 90s. Mathematically, people have shown that an ensemble theoretically is going to produce better results compared to a dedicated model, no matter how the model has been trained on the data. And there has been a lot of work again, empirically, different kind of applications which has shown that ensembles perform better than simple models, dedicated models which have been fine-tuned on the application. The creation of an ensemble basically consists of two steps. The first step is to decide how you are going to create the individual members of the ensemble, the different models. Okay, the different models are called members of the ensemble. So you can use different techniques, and I will give you some examples next. The other idea is has to do with how you're going to combine them. Okay, you find a way to train all these different models. How do you combine the results of this model? Each one of these models is going to give you different results. You need to have a way, a function that will take into account the outputs of the different models and make a decision. That will be the final result. So you need a kind of combination of aggregation of the outputs in order to produce the final output. The idea behind ensemble is based on this notion of weak learnability that was introduced in 1990. Up to that point, people were trying to create the optimal model in a sense. Okay, so they were trying to fine tune it. There are, as you see, different kind of parameters. There are parameters that relate to the architecture of the model. There are parameters about, the training algorithm that you use. And there are so many different models and so many different algorithms, which makes it a very complicated problem in reality. So the idea of weak learnability was that Saperi showed that it is possible to produce very good results without necessarily using a very strong model. Okay, so you can have a model that makes errors as long as your model behaves reasonably well, more than 50% in a sense, 55, 60, 65%, then you can use this kind of model that you have produced as a base model and build an ensemble. And the ensemble, he showed, is going to perform better than the best model that you have. Okay. And this kind of idea led to the development of different kind of algorithms. And we have algorithms that use the notion of boosting. It's one of the methods that I'm going to explain. Bugging, there are different kind of techniques. So Sapiri introduced this idea, the concept of weak learnability, and used this kind of concept to derive a whole theory for boosting. He started with binary classification problems and then moved later to multi-classification, multiple classes, and also examined in his work batch learning and online learning and different kind of modeling frameworks. And there is a strong mathematical theory behind boosting. So in an ensemble, basically what we have is something like that. We have a sequence of networks, a set of networks. These are the different members of the ensemble. These are trained in different ways. You can train them. There are different ideas about how you can train them on input data. And then you calculate the outputs and you combine these outputs to produce the final result. And people have tried in the literature different techniques. It's the basic way is what I call here the simple network ensemble. So you have a pool of models and networks. Each network has used the full training set for training. The models are different in the way they have been initialized, for example. So you can have a pool of models of neural networks that have been trained on the same data, but they have been trained with different initial weights, and these networks would be combined to form an ensemble. Okay, one of the problems, if you have tried this kind of method, one of the problems that you have is that usually it doesn't work very well. You can get an improvement, but it's a very small improvement. It's not the best idea, the best technique to use, if you want to create an ensemble. There are much, much stronger methods for creating neural ensembles. And also ensembles, because these kind of techniques can be used also to create ensembles of other methods, as I said, decision trees. One of the methods is, random forests. Random forest uses this kind of idea of it creates an ensemble of decision trees. So the more advanced approaches use ideas like bugging. In bugging, you produce subsets of the training set, and you use these subsets to produce a training set by sampling from these subsets. And you do resampling with replacement of the original data set with a uniform probability distribution. Or there is this kind of idea which is called boosting. Boosting also uses resampling of the original training set, but the weight by which you do the resampling, it depends on whether the data points have been classified successfully or not. It's a very interesting idea. It basically gives higher weight when you do the sampling to data points that have produced mistakes. Okay, and that helps at each round of boosting to produce members of the ensemble which make a contribution. They are better. They are dealing with mistakes of the previous members of the ensemble. And another idea which always works, is very strong concept. It's the notion of diversity. You create the so-called diverse network ensemble. In diverse network ensembles, the members of the ensemble are allowed to make mistakes, but they have to disagree on their decisions. It's an interesting concept. You put networks in your ensemble that make mistakes, but they make mistakes at different input data. Yeah. This is the notion of diversity. And then as you have a large number of networks, the majority of these networks will give you a very good result. So a few things about boosting, as I said, introduced in the 90s, and then we had one of the algorithms that is still very popular, AdaBoost, introduced in 1996 in the paper Experiments with a New Boosting Algorithm. And this is the AdaBoost that is, there are different versions of AdaBoost. You can find it in most of the tools that we have today, toolboxes. Okay, so what's the idea? The idea is that you have models. These are called learners. They are trained sequentially using a sample from the original data set. But you use the error that they are making, the models, at the previous round to influence the sampling weight of the data points for the next round. So at each round of boosting, you have to decide whether you're going to terminate or use a new set of calculated weights to continue, or you terminate and you assign weights to the different members of the ensemble, and you combine the decisions in order to make a final decision. That's roughly the idea. And I have here a high-level description of a general boosting algorithm. There are different kind of boosting techniques that one could use, and in the literature, if you Google about boosting, you will find many different algorithms. So what's the idea? Every boosting algorithm has some important stages, and depending on how you implement this kind of stages, you can produce different variants of boosting. Okay, so an important parameter that you need to consider is how you build these distributions, the subsets, how you sample the data from your training set. Okay, so there is a step here which is called pick from set. Okay, so you have the whole set, and you have to somehow define a kind of probability distribution or a distribution of weights, because this probability distribution is used to sample weights, to sample points from your training set. Okay, and you can do that in different ways. So you can produce different techniques to produce these weights and calculate this distribution D. Okay. Another important thing is how you are going to train the new classifier that you are going to produce, the new member of the ensemble. Okay. So you are doing the resampling. You have a new subset that you can use to train a new classifier that's HT. This classifier is going to contribute because it will be trained on some kind of data points that are going to, that previous classifiers produce poor results. Okay, so it's going to enhance the performance of the ensemble. Basically, it's going to reduce the classification error of the whole ensemble. That's the idea. And you calculate the error that the new member produces. That helps you to again calculate another weight. This is called A, which is the contribution of the particular member of the ensemble into the aggregation, how the decisions of the different members of the ensemble are going to be taken into account. And you have the important step, this one here, when you update the probability distribution, the equation of the probability distribution. So the next distribution depends on the distribution that you currently have, on the performance of the network that you produced, on the weights and the whole data set that you have. So you update the parameters of the distribution. Its distribution is represented by a function, by an equation, basically. Okay, and the equation has some parameters which is updated in this step. So the next distribution is an update of the parameters of the probability distribution that selects weights, selects data points from the whole training set. Okay, the selection of the data points depends on some weights, and the weights are specified in a way that are bigger for data points that the classifier, the previously trained classifier, had poor performance, smaller weights for data points that were successfully classified. They had small errors. That's the general idea. That's another technique that was introduced in 2016. It's called deep incremental boosting. It uses the idea of boosting, but it combines the idea of boosting with ideas from transfer learning. In transfer learning, we use models which have been trained on a particular kind of training set. We reuse components of these models, part of their layers, several of these layers, but this new model is trained on a new kind of data set, okay, to learn a new domain, a new application domain. So we can use this kind of idea to reduce the complexity of the whole problem, and this is what deep incremental boosting does. So you have the so-called base model, which is a multi-layer deep network, a deep network with several layers, and that was produced with the original data set, the whole training set at the beginning, and it has a performance. As with boosting, you need this model to behave, to have performance of at least 55, 60, 65%. Okay, and you have the base model, which is the result of round one of the boosting. Then what happens is that you apply boosting, so you use the idea of the probability distribution to select with higher weight data points from the training set that resulted in poor performance of the base model, and you create a new model, a new member of the ensemble. The new member of the ensemble consists of a copy of the base model plus an extra layer. Okay, and you can use this kind of idea with different kind of architectures. You can use convolutional neural networks, so the base model can be a convolutional neural network, or you can use it with residual networks. So the different layers are represent blocks of residual blocks. Okay, the dimensions of the capacity or the number of layers of the new network that is produced at each round of boosting is bigger. So you add an extra layer here, but computation is not expensive because all the previous layers come from the base model. So you only have to do minimum training, as I'm going to show you next. And you can continue like that at each round of boosting. Okay, this idea is called deep incremental boosting. We introduced it in 2016. And you can see what happens with deep incremental boosting. These are results on some benchmark data sets in terms of in testing. These are standard benchmarks, MNIST, CIFAR-10. This is with augmentation, CIFAR 100, and again with augmentation. This is AdaBoost, what's going to give you performance. This is our performance from 10 runs. And you have residual network, similar kind of in terms of complexity. Residual network. This is deep incremental boosting and with convolutional neural networks, layers of convolutions. And this is the boosting residual network. So it's a residual network together with boosting. Okay, and you can see that the performance it's the same or slightly better actually with the ensemble compared to boosting, which is again an ensemble, and a residual network. Okay. Someone would say, okay, so what's the point if a standard residual network gives you more or less the same results? So what's the point of trying, the ensemble? Before answering that question, that's a schematic of how this deep incremental boosted ensemble would look like. So you have the base model, which was designed in round one, and then you have the second round of boosting. You have the base model plus the extra block. And at each round of boosting, you have the base model plus the extra blocks that you have produced, and you aggregate. Okay, and these are different kind of blocks, the blocks that we used for MNIST and the CIFAR-10. Okay, so these are the additional blocks. This is how the additional blocks look for MNIST and CIFAR-10. These are for convolutions. Okay, deep incremental boosting with convolutions. Okay. If you use residual networks, then you have to have residual connections, skip connections as well. Okay. So why this thing is interesting? It's interesting because of this result. This table gives you the training times. Okay. So you can see that the training time of incrementally applying boosting actually makes sense. As I showed you, the performance is the same or better than using AdaBoost or using, a very good residual network. But look at the training time it takes to produce this kind of results. Okay. You can see that although we are using an ensemble, AdaBoost is an ensemble technique. You see that the training time does not increase significantly. Okay. This is the training time that the base network took to produce. Okay. And this is the time that the ensemble took to produce. When you use deep incremental boosting, where you have base networks, these are the networks with convolutions, convolutional neural networks. And this is the BRN is the ensemble where you use residual networks. Okay. And you can clearly make the comparison between the residual network of the same kind of performance and the time it took to train it and the time it took to produce the ensemble. Okay. It is much faster. The time to train the base network and the residual network of comparable performance to the BRN. Okay, it makes sense. Okay, you can have at least the same performance or even better, but the training time it's much faster. The other idea that I mentioned to produce ensemble is this notion of diversity, which in the beginning sounds strange because you allow the models that you have to make mistakes. In boosting, we said that each member of the ensemble that is produced at each round of boosting, each classifier, it is trained on the mistakes on the data points that the previous models failed to classify properly. Okay, so basically what boosting does is that it says, look, no, we have to try to minimize the errors. So the notion of diversity is quite the opposite. It definitely tries to minimize the errors, but it says at the same time, like, look, it doesn't matter, you can allow errors. Okay, so as long as you make sure that the models produce errors at different inputs. Okay, that's the whole idea. And a simple way to do it would be to create a number of networks, use the same set, training set, vary some parameters like the weights, and then from the pool of networks that you have produced, select a subset of networks that, although they make mistakes in the classification of the data, they fail on different input patterns. Okay, so the pattern of failures of one can be compensated by the successes of the other, basically. Okay, and you combine these models. Another idea to do it, which is again simple, is to use to produce different subsets of the training set and use these subsets to produce the pool of models and then select from these ones the ones that make mistakes at different inputs. And it's a simple way to create the ensemble. And I have an example here to show you the use of the diverse ensemble in a problem. The data set actually, it's not big. It's a small data set because it's based on bioinformatics. It's a problem where you don't have a lot of data and you have to deal with class imbalance. You have a small number. Each one of these data points is a result of an experiment in biology where you collect information. So the data set is small because you cannot run a large number of experiments. Each experiment costs. There's a cost associated with each experiment. So the data set is small. But you can see what's the problem. The problem is that you have different kind of proteins. The proteins are localized at different sites, localization sites of the cell. And the problem is that they belong to different classes. And you see that some of the classes have a large number of examples. Some other classes have a much smaller number of examples. So you have 5 here, 20, 30, 463 there. Okay, so it's drastically imbalanced. You have classes which have a very small number of data points. We know that there are different ways to deal with class imbalance that have been proposed in the literature. One of the best methods is to use ensembles to deal with class imbalance. Okay, and they give you a lot of flexibility. And this is what happens here. We use diverse ensembles to deal with this kind of problem. And these are some results. You can see the performance for each one of these classes. This is HN is a model in the literature. It's based on probability. It's a probabilistic model. HN is the initials of the guys who introduced the model, the Horton-Nakai model. It's called HN. It's a probabilistic network. KNN, classic K-nearest neighbor. FNN is a multi-layer neural network, and DNE is a diverse ensemble of diverse neural ensemble. And you can see the behavior. The performance increases as you move from probabilistic models to neural networks. In general, neural networks, and particularly ensemble of neural networks, are now standard in these bioinformatics databases, which do processing of proteins. They try to recognize different kinds of proteins or genes, etc. Most of these databases, bioinformatics databases, are based on neural ensembles. So that was the lecture for today. You will find material on about neural networks on chapters 6.1 up to 6.5 in the textbook. And then I have specific chapters for recurrent networks, material which is in material online. This is the paper that introduced backpropagation in time, through time, 1990, WebOS, what it does and how to do it. It's available online. This is another approach for online training of recurrent networks by Williams. It's an incremental learning of recurrent neural networks online. And for ensembles, some online sources on the methods that I covered, ensemble learning in general, the diversity, a very important paper from 1995, the notion of ensembles. This is a paper, the work that we did with diverse ensemble on the localization sites of proteins. And this is one of the latest papers we published on this idea of deep incremental boosting in the neural computing applications. You can find it online. You can download it. Next week, I'm going to continue with a different topic, genetic and evolutionary algorithms. And you can have a look on the chapter 7.1 up to 7.6 from the textbook if you want to prepare for this lecture. I'm going to start with genetic and evolutionary algorithms in general, and also in another lecture later, I'm going to explain how these ideas have been used to train neural networks. This kind of global optimization, global search algorithms can be used to train and optimize neural architectures. And in my opinion, this is, the next step forward toward the direction of, for neural architecture search, so that we can automatically design machine learning algorithms and automatically build neural architectures, because otherwise the complex becomes much more complicated. And we have to deal also with the inefficiencies of the gradient descent method. Still, most of the packages that we have today, libraries, are based on this kind of idea of gradient descent, etc. So that was the topic for today, and I'll see you in the live session as well to talk about these issues again. Okay, so bye for now.